Talking about effusion and diffusion is always kind of interesting. There is some idea people usually have of what diffusion is, but effusion is kind of a term most people haven't heard before. So let's talk about what each of these things is first before we get started on any kind of calculations. Effusion, if we take our little balloon picture over here, can you all recognize that as a balloon? I'm such an artist. Oh my goodness. Yes, we've got a little pinhole, and I'm going to make a little dot on the side of the balloon to show that that's where our pinhole is. And so effusion is how fast can a particular gas get through that pinhole to escape from the balloon. I've got a mixture of gases in there. I've got little circles, I've got dots, and I've got triangles. And the different kinds of gases are going to effuse out of the balloon. They're going to escape through the pinhole at different rates. And that rate is going to depend on their molar mass. How heavy you are has something to do with how fast you can move. The second picture is a picture for diffusion. We've got, again, three different kinds of gases in here. I've got little triangle gases and X gases and dot gases. So with diffusion, I want to know how fast a molecule on one side of the container can get through the crowd over to the other side. Now, the arrow that I've just drawn is like a straight path, and that's not actually what happens when they're trying to, when they're moving around. All of these molecules are moving at somewhere close to, very, very roughly, about 1,000 miles an hour. Okay, when you think about yourself going 1,000 miles an hour, that's pretty fast. And not only that, but they are, on average, very, very roughly again, having about 1,000 collisions per, guess, what do you think, per second. Oh my gosh, that's a huge number of collisions. So in order to actually go 1,000 miles an hour, and having 1,000 collisions a second, you think about how many collisions there are in an hour, that would be an enormous number. So they are actually going through a very jagged path because they're bouncing off of each other, and his path to get from one place to another is actually a very disjointed kind of bouncing all around path. Think of a pool table with all of the balls in 3 dimensions. So you break the balls and they start flying about the room and banging into each other and the walls and having 1,000 collisions a second. It's a pretty torturous path to get from one end of the thing to the other. Again, how fast a gas gets from one side to the other will depend on his size. If he's bigger, he moves slower. If he's smaller, he moves faster. And so we have one equation that works for both of these cases, escaping through the pinhole or just getting through the crowded ranks of all the other gases in my way. So if I say the rate of molecule A, and I'm going to compare that to the rate of molecule B, then on the other side I have to take the square root of the whole thing, and again it's the molar mass. Remember, that's the script m onto the molar mass of one compared to the molar mass of the other. But we just said that the smaller ones move faster, right? Smaller ones move faster. So you see that we had A on top and B on bottom. Now we have B on top, A on bottom, because the faster you move, you have to have a smaller molar mass, and if you have a bigger molar mass, you'll go slower. So that's why the A and B is upside down from each other in this rate equation. Okay, so molar mass. Now, here is a tricky little thing that we need to talk about. Since the rate is usually expressed in terms of concentration over time, are you all aware that this square brackets I put on top of that fraction, that square brackets means concentration, okay? Usually in molarity, concentration in terms of molarity. But I'm going to use that square bracket symbol to symbolize concentration. So we can actually substitute in, if I have rate of A over rate of B, I'm going to put in concentration of A over the time A takes to move, or to effuse, or to diffuse, And that's over the rate of B, but rate of B is the concentration of B per its time. Okay? And if I go ahead and invert and multiply like I'm supposed to do with fractions when I am dividing them, I have the concentration of A over time of A, and then I will have that times the time of B over the time of A. Oh, sorry, concentration of B. I looked away for 1 second and wrote the wrong thing. Okay, over concentration of B. I hope you can all read that. Okay, so there we go. Now, in most of the problems that you'll see where we're dealing with time instead of rate, they don't tell you the rate, they tell you the time. They'll give you equal concentrations. If you're going to set up an experiment with this, and you're going to try to measure something, you would want to put the same concentration in of the two gases into your chamber and watch their effusion or diffusion rate, because then you're holding something constant, and that makes it easy. If A equals B, concentration of A equals concentration of B, then we can just cross those out, and we end up with something like this. We get the rate of A over the rate of B equals, and now what do I have left? I have time of B on top over time of A. And so look at that. They're opposite of each other again, A and B. So now I'm going to take this time A, time B thing, and I'm going to substitute it back in to my equation up there. And I'm going to have then time of B, the time it takes B to effuse out of through our pinhole, or the time it takes to diffuse through a crowded container, and then I'm going to set it, of course, equal to what it was equal to before, B over molar mass of A. So notice, in my first version, where I'm using rates, the A and B are upside down from each other. In the second version, where the problem has times in it instead of rates, the B's line up with the A's. So you go upside down with rates, you don't with B's, and then you can solve the problem. So let's set up a problem. We're going to do a sample problem. We're going to say we have an unknown gas. Okay, UNC. UNC is our unknown gas. It's going to effuse in 11.1 minutes. All right. We're going to compare it to a known gas, something that we know what it is. I'm going to choose hydrogen. And hydrogen, under the same conditions, same concentration in the same container at the same temperature, is going to effuse faster. There's not much that's smaller than hydrogen, so we would expect hydrogen to effuse faster because he's going to be smaller than just about anything. And of course, what we're looking for is the molar mass of our unknown. So what is UNC's molar mass? That's what we don't know. We're going to use which one? Which equation? Let's see. We don't have a rate, do we? So we can't use the top one, the top boxed equation. We're going to use the bottom one because we do have times. So that means that times are going to line up with the molar masses on top and bottom. I don't know my unknown, so I'm going to label the unknown as B, and I'm going to label hydrogen as my A. So I'm going to put the time of B on top because that's what my equation says. 11.1 minutes over 2.42 minutes, and that's going to equal the square root of the molar mass of our unknown, which we don't know, and the molar mass of hydrogen, which we do know. Hydrogen is a diatomic molecule, so it's 2.016 grams per mole. And so when we rearrange, we're going to take we're going to end up with the square root of the molar mass of B, and that's going to equal 6.51. Now when I take this, I'm going to have to square both sides, right? Square both sides so that I can get rid of that square root symbol. And now the molar mass of B is going to be 42.4 grams per mole. And there's my answer. This is a pretty handy thing to be able to do. Is you've got a gas, you don't know what it is. one of the first things you want to know about it is, hey, what's its molar mass? It's going to help you to determine what the gas is, and it won't be unknown anymore. So that's a good thing.